All right, let's try this again. So this is Unit 6, Section 2. We're talking about polynomials. So the graph of a polynomial function is a continuous curve. So if you look at this one, it is not a polynomial because it has gaps. So there's a gap here, here, here. So when it has gaps, it cannot be a polynomial. So that's a no-go. So not a polynomial. This one is not continuous. So this one, on the other hand, look how pretty this is. It has no breaks, it has no gaps, no holes, no nothing. So this is a polynomial. It is continuous, no gaps. All right. So now here is another polynomial we have. We have the graph and we have the function written out right here. So we have the left side and behavior. We're talking about this guy right here. So when we look on the left, the polynomial is going forever and ever this way, in this direction. And the right side and behavior, we're looking at this guy right here. It's going forever and ever this way. It will continue going that way. So that's why it's called right side and behavior. Now, when you're taking your SAT, your ACT, you will have questions that will say, describe the end behavior of the following function. And you actually need to know what they're trying to ask. And this is exactly what they're trying to ask. So left side end behavior, as x approaches. So this arrow means approaches. So you read as x approaches negative infinity. So right there, x is approaching negative infinity because it's going all the way over to the left. Then f of x, or y, approaches what? Well, approaches positive infinity because see how it's going all the way up to positive infinity. So as x approaches negative infinity to the left, then f of x, or y, approaches positive infinity. That's what they're trying to ask you. That's what they mean when they're asking you about, determine the end behavior of this function. Not only the left, but also the right side. So the right side end behavior you have as x approaches positive infinity, so it's going to the right here. Then f of x, or y, approaches negative infinity. It's going down right there. Now, we have the negative leading coefficient. It behaves in a way. And we also have the odd degree of this polynomial, because 3 is odd, 3 is not even. We also know the x-intercepts right here. It's where your graph crosses the x-axis, right here, and right there. We also know the y-intercept. That's that point right there. And we have the minimum and the maximum points. Minimum, maximum. Okay, not bad. So here's another one. We're going to start talking about the left and the right side end behaviors, just because I'm going to try to follow the same order. So the left side end behavior, I'm looking at this right there. So as x approaches negative infinity, because it's going to the left, then f of x, or y, approaches negative infinity. Well, it's going down towards the negative side of the y. So as x approaches negative infinity, then f of x approaches negative infinity. The right side end behavior, as x approaches positive infinity to the right, then f of x approaches negative infinity. Notice how they're matching. And because they're matching, this is the relationship right here. So we have an even degree right here of the polynomial. So degree 4, they match. So negative leading coefficient, it means they're pointing down. X-intercepts, we have all of these, the points where your graph crosses the x-axis. Now we not only have a minimum, but we have a local minimum. So it's the minimum point because otherwise these guys would be the minimum, right? But we won't have an absolute minimum because it the arrows indicate continuity right there. So we only have the local minimum. That's the lowest point where your graph is within that region. So the maximum, in this case, we have the absolute maximum. So it's as high as your graph is going to go. It's not possible to go beyond that. So the absolute maximum it can go is that guy right there. And then the local maximum, okay, this is the maximum, but it's just within that region. I have the absolute maximum and I have the local maximum, that it's a maximum, but it's not as good, I guess, as the absolute maximum. So minimum, maximum and minimums. So just like the quadratic function, polynomials can have maximum and minimum values. Unlike quadratic functions, there's more than one because it's a polynomial, so you will have more than one minimum or maximum. So when referring to a group of maximum and minimums together, in general, we call extrema or turning points. Depending on what book you're following, you can see either way asking about the extrema or turning points. So we already talked about the absolute maximum a little bit. So it's the point where the function obtains its greatest possible value. So you can't go beyond the absolute maximum. That's as high as your polynomial is going to go. That's the absolute maximum. And the same idea applies for the absolute minimum. It's the lowest possible value of your polynomial. Now, the local maximum is the point where the function is locally the highest. Okay, it is the highest at that point, but it's not the absolute maximum. This is the absolute maximum. And the local minimum, same idea, it's locally the lowest point. So local extrema cannot occur at endpoints because they can only occur in open intervals. Okay? Cannot. And there's a question on the college homework about this. Okay, this is very, very colorful. I like it. So I'm going to zoom in because you kind of need a magnifying glass to read this graph, but off we go. Okay. So this graph is very similar to the one we just did. I tried to color code it so you know where I'm finding the information. So absolute maximum is that guy right there. So the y value is a little bit above 7, so 7.5. The absolute minimum, we don't have it because it keeps on going forever. So there's none right there. Local maximum is the highest point, not the absolute maximum, but you know, it's the max point right there. So local maximum is that guy right there. So it's a little below 3. So y equals 2.8, 2.75. That's close enough. Local minimum, that guy right there. So y equals negative 0.5. And I know your paper doesn't say that, but the number of extrema is kind of important because it will directly connect to the degree of the polynomial. So we're going to count. So the number of extrema, 1, 2, 3, or the number of turning points. So 3 right there. Okay, the next one, absolute maximum. We don't have an absolute maximum or absolute minimum because they keep going. That indicates that keeps on going, so we don't have the absolute maximum or minimum. So none for both of them. Local maximum, we're going to have 2 in this case, this guy and this guy. So it's this one is about 3 and this one is about 0. It's pretty close to 0. The local minimum, we have these guys. So this one seems to be a little bit lower than this guy. That's why we chose to do negative 1.25 or negative 1.2. But this one is right there at negative 1. And number of extrema, we have 1, 2, 3, 4. Okay, one more. Right there. I have the absolute maximum, that guy. So y equals 5, right there, easy. Absolute minimum is this guy right there. So it's purple right there. So absolute minimum at y equals -4 right there. So local maximum, we don't have one. It would have been that one, but it's an open dot, so that doesn't count. So none for that. Local minimum is also that one. Just like the absolute minimum, local minimum, they're both right there. So y equals -4, and number of extrema, because it's a quadratic function with restrictions, of course, it's only one right there. So here I have absolute maximum is that guy, a little less than 1. So a little less than 1, we got that. Absolute minimum is that one in purple. So y equals -1.25, -1.3. Yeah, little below -1 right there. So local maximum, that guy right there. So a little above. It's more than 0, but it's less than 1/2. So that's why we're going with 0.25. It could have been 0.3 if you would like. Local minimum, we have 2 right there, and I have -2.25, 0.25 right there. And here it's a little less than 1, so -0.75. Number of extrema, 1, 2, 3. Okay, the turning points are right there at 3. Now, turning points. There it is. A turning point is a point where the function changes direction. It's also extrema. Let's practice. Let's find the turning points for the following functions. So turning points, right there, right there, right there. Here, 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 here. And then this one, we don't have a graph yet, and we don't have a graphing calculator, so we'll come back to this later. I mentioned earlier that the number of turning points or number of extrema actually relate to the degree of the function. So the number of turning points is always 1 less than the degree. So whatever the degree is, you take away 1. Example, this one we have 3 turning points. So that means the degree of this one would be the 4th degree. This one, 1, 2, 3, 4, and this one will be 2. But we will get into the details a little bit further into this video. Okay, end behavior. So we talked a little bit about the end behavior of a polynomial by looking at the graph, but the formula of a polynomial can tell us all about the end behavior, and it can actually predict, and you can go back and forth between the function and how to graph it. So we need to pay attention to the leading coefficient will determine the end behavior, and also the degree of that polynomial. Here is what we need to know. So if we have even functions, so that means degree 2, 4, 6, and so on. So anything with even degrees. So when a is less than 0, or the leading coefficient is negative, a is the leading coefficient. So negative leading coefficient, we know both ends of the graph will go down. It's going to point down like this. Now, if a is positive, or positive leading coefficient, both ends will go up. Both ends go up. When the leading coefficient is positive, both ends go down when the leading coefficient is negative. Now, as x approaches -infinity, then f of x approaches -infinity right there. So the first one, we're looking at this guy. So as x approaches -infinity, f of x, or y, approaches -infinity. As x approaches positive infinity, so we're looking at this guy now, then f of x approaches -infinity. So they both go down. Now, when the leading coefficient is positive, as x approaches -infinity, we're looking at this guy, -infinity, then f of x approaches positive infinity. So y is going up toward positive infinity. As x approaches positive infinity, then f of x also approaches positive infinity. They both go up. Now, odd functions, they're a little bit different. So all the odd functions kind of behave the same way. So linear, cubic, anything even functions, they will behave the same way. So when a is less than 0 or negative leading coefficient, then the left side goes up. This is the left side, goes up, and the right side goes down. Right side goes down. So left side up, right side down. A good way for you to remember is positive and negative slope. So positive slope, so a linear function behaves this way, same way as any other odd functions. And negative slope goes down like this. So anything, that's a good way for you to remember. So as x approaches negative infinity, then f of x approaches positive infinity, this guy. So as x approaches positive infinity, we're looking at this. As x approaches positive infinity, then f of x approaches negative infinity when the leading coefficient is negative. When the leading coefficient is positive, then the left side goes up, the left side goes down. This is the left side. Left side goes down, right side goes up. So as x approaches negative infinity, then f of x, as x approaches negative infinity, then f of x approaches negative infinity. As x approaches positive infinity, then f of x also approaches positive infinity. Right there. This is only true for positive leading coefficient. I will come back and I'll make another video for the rest.